This video I'm presenting my iClear work titled Learning Distributions of Complex Fluid Simulations with Diffusion Graph Networks. It's co-authored with Tobias Paff from Google DeepMind and Niels Tugge, my supervisor at TUM. Our interest here was in physical systems posing complex and unsteady dynamics. Fluid flows are a clear example of this. For instance, here we have the time evolution of pressure on the surface of three different wings. It's clear that in this case a single time average solution per system is not enough to represent the dynamics of these systems. Instead, we will need to have access to all the possible states the system is visiting through time, with which we could compute relevant statistic metrics. The standard approach for this relies in expensive simulations of long trajectories. And although deep learning based surrogates have been available for a while, these often became unstable while producing long rollouts. So we decided to follow a different approach and leverage diffusion and flow matching models to learn the distribution of fully developed flow states from data. With these models, once they are trained, we can evaluate them with the domain geometry, boundary conditions, and physical parameters as input, and we obtain as output the physical fields defining the state at a certain time point. Importantly, we cannot control at which time point we obtain the solution. However, if we evaluate the model multiple times with the same conditioning inputs, then we obtain a collection of states that could also be used to compute the statistic metrics that we were interested in. In CFD, we often use unstructured meshes to represent complex geometries, so similarly we decided to use a graph-based representation and process the data using a graph neural network. One key finding of our work is that diffusion graph nets are able of learning full distributions even when trained on partial distributions obtained from short and incomplete trajectories. This significantly reduced the data generation cost, especially for 3D turbulent flows, since the trajectory for each of the geometries in the training data can be much shorter than what would be required to capture the whole fluid flow diversity. We follow the improved DDPM framework, but instead of applying it to images, we apply it to physical fields defined on the node of a graph. Here we have from right to left the diffusion process where noise is added following a prescribed noise schedule, and from left to right we have the denoising process where each of the denoising transitions is a Gaussian parameterized by our diffusion graph net. This network takes as input the physical fields at the current time point. This is the noisy physical field, the index for this current denoising step, the connectivity of the graph, and we can also have node and edge features that condition to a certain system in particular. For instance, we can have at the nodes the Reynolds number, and at the edges we can have the relative positions between the sender and receiver nodes of the edge. The output of the network are the noise epsilon with respect to the reference and the interpolation parameter b, both used respectively to obtain the mean and the variance of each Gaussian transition as proposed in the improved DDPM paper. The graph neural network that we use follows a multi-scale architecture, which means that message passing is applied to the original graph but also to multiple coordinates of these ones. Particularly, we follow a unit-like architecture like the one depicted here. So, besides message passing, we also need graph pooling and unpooling layers. With graph pooling, we are compressing our input mesh into meshes that could look like these ones, for instance, for this wing geometry, and we can see that in the bottleneck of the network, the graph or mesh is quite small. And we found that actually we need to use this kind of multi-scale architectures because when denoising, each of the denoising transitions has to be able to remove high frequency noise but also low frequency noise. And for this, we need a large or even global receptive field. And it would be very expensive to achieve this just by stacking message passing layers, particularly if we have a very large graph. Now that we have our diffusion graph net and we have trained it, we can map a sample from a Gaussian distribution to a physical field. For instance, in this case, we obtain the pressure field on the surface of a wing. Nevertheless, you may notice that there is some residual noise at the end of the denoising process. And also, each of the denoising transitions had to be applied to a very large graph, so this can be expensive. To mitigate these issues, we follow a common approach in deep learning, which is applying the diffusion graph net to a compressed latent space. This compressed latent space corresponds to that in the bottleneck of a variational graph autoencoder, which also follows a multi-scale GNN architecture. And in the case that we have two graph pooling layers, for instance, then in the bottleneck we have a compression mesh looking like this one, where we are going to be applying the diffusion framework. Our BAE has three building blocks. First, we have the condition encoder, which takes the conditioning features for the nodes and the edges, like Reynolds number, relative positions between nodes. And with this, we generate compressed encodings of this for the nodes and edges on each of the lower resolution graphs. These conditionings will be used by the node encoder, the node decoder, and also later by the diffusion graphnet. Then we have the node decoder, which takes as input the physical fields in the dataset and is going to generate latent features at the nodes of the compressed mesh. And then we have the node decoder that allows us to go back to the physical space. Once we have trained this BAE, we can train in that latent space the diffusion graph net, and at inference time we combine both of them and evaluate them following the pipeline indicated in this diagram. So we can see that first we evaluate the condition encoder from the BAE, then we sample Gaussian noise on a compressed mesh, and we gradually transform that noise into a sample. And finally, we have the node decoder that takes this sample from the latent space to the physical space. And there are two things that we should point out at this point. So first, the diffusion graph net is applied to a compressed mesh, so it's going to be faster than directly doing in the physical space, and also the condition encoder and node decoder are relatively small and only evaluated once. Also, secondly, the node decoder has been trained as part of a beta BAE, so it's robust to noise in the latent space, which means that if there is some residual noise at the end of the denoising process, when we go back to the physical space, the node decoder is able of filtering out and results into high quality samples. We tested our diffusion graph nets on three tasks. First, we consider the two-dimensional laminar flow around an elliptical cylinder. This ellipse can have different thicknesses, and we also consider different Reynolds numbers. The first task consists on inferring the pressure profile on that ellipse. The second task consists on inferring the velocity and pressure profiles around the ellipse. And the last task consists on inferring the pressure on a wing under 3D turbulent flow. Here the wing can have different geometries. Since we were interested in the ability of these models in learning from partial distributions, each of the training trajectories in the first two tasks only contain 26 to 48% of the vortex shading period length. And for the last task, each trajectory had like a 10% of the time steps that we will need to have converged standard deviation. Let's have a look to the sample accuracy of the models. So for the latent diffusion graphnet, we have here two samples generated. These are in blue, and in black we have the ground truth, so very good agreement. Here we have for the second task the velocity field around the ellipse. So we can see that the diffusion graph nets outperform other baseline models, and importantly, the latent variant of the model doesn't have some of the residual noise that was present in the diffusion graph net. This was also confirmed in the third task, where the latent diffusion graph net produces more accurate fields. And this was also quantified using the graph Fourier transform of these generated fields. What we were more interested on was in the distributional accuracy. To test this, we have to evaluate our probabilistic model multiple times to obtain a probability distribution for each geometry in particular. If we plot the probability cloud for the states used in one of the training trajectories, then we have a probability cloud like this one. Whereas if we consider the probability cloud for the full trajectory, this is for a whole vortex shading period, then it looks like this. Now, if we evaluate the latent diffusion graph net multiple times to obtain different pressure profiles for this first task, the probability cloud that we obtain for all the solutions looks like this. So interestingly, the latent diffusion graph net was able to learn the full distribution when trained on this kind of short trajectories. This is very important for reducing data generation cost, and we also found this in the 3D turbulent case. For instance, here we have the standard deviation of the pressure along one of the training trajectories, and for a 10 times longer trajectory, then the standard deviation looks like this. Here it has already converged. And the latent diffusion graph net was able of inferring a standard deviation similar to that real standard deviation instead of predicting something similar to what what it is in the training distribution. This is also true for unseen geometries and Reynolds numbers, and importantly, diffusion graph nets weren't the only baseline models able of learning these full distributions from partial training data. We can see here that Bayesian, Gaussian mixture models, or even BAEs were struggling at this. Here we have the same for the wind task. We have here the standard deviation predicted by the Gaussian mixture model, which is quite different to what we should be expecting based on the ground truth, and the diffusion graph net and latent variant are doing a much better job. Now, how do our diffusion graph nets perform? If we consider the task of inferring the pressure on the surface of a wing, then with OpenFOAM running on 8 CPU threads, we will need a bit more than 2 days. Whereas with our latent diffusion graph net on the same hardware, we just needed 49 minutes. And if we use a desktop GPU, then we just require a couple of minutes. Another possible application of our diffusion graph nets is to directly obtain a fully developed flow solution that can be used as an input condition for a high fidelity solver. So in this case, we are replacing the numerical solver running through the warm-up or transient phase with a single evaluation of the solver. And the acceleration that we obtain is huge, 4 to 5 orders of magnitude. The latent version of our model is also 8 times faster than the diffusion graph net for this task. Also, this of course depends on the compression ratio for the latent space. And also, if we switch to flow matching like we did in later experiments, we can even obtain better computational performance. So that's it. Here we have some highlights to conclude. We have seen through this presentation that with diffusion graph nets we can directly map geometries to fully developed flow solutions. If we evaluate these diffusion graph nets multiple times, then we can approximate the probability distributions. And we can do this even if the trajectories that were used for training were quite short, what is very important in terms of reducing the data generation costs. And the latent version of the diffusion graph net offered higher sample accuracy, higher distributional accuracy, and it was also faster. So that's all. Thank you very much for your attention.